In probability theory, the law of large numbers is a theorem that describes the result of performing the same experiment a large number of times. According to the law, the average of the results obtained from a large number of trials should be close to the expected value, and will tend to become closer as more trials are performed. The LLN is important because it guarantees stable long-term results for the averages of some random events. For example, while a casino may lose money in a single spin of the roulette wheel, its earnings will tend towards a predictable percentage over a large number of spins. Any winning streak by a player will eventually be overcome by the parameters of the game. It is important to remember that the LLN only applies when a large number of observations are considered. There is no principle that a small number of observations will coincide with the expected value or that a streak of one value will immediately be balanced by the others. Examples: for example, a single roll of a fair, six-sided dice produces one of the numbers chapter 1, 2, 3, 4, 5, or 6, each with equal probability. Therefore, the expected value of a single die roll is according to the law of large numbers. If a large number of six-sided dice are rolled, the average of their values is likely to be close to 3.5, with the precision increasing as more dice are rolled. It follows from the law of large numbers that the empirical probability of success in a series of Bernoulli trials will converge to the theoretical probability. For a Bernoulli random variable, the expected value is the theoretical probability of success, and the average of n such variables is precisely the relative frequency. For example, a fair coin toss is a Bernoulli trial. When a fair coin is flipped once, the theoretical probability that the outcome will be heads is equal to 1/2. Therefore, according to the law of large numbers, the proportion of heads in a large number of coin flips should be roughly 1/2. In particular, the proportion of heads after n flips will almost surely converge to 1/2 as n approaches infinity. Though the proportion of heads approaches 1/2, almost surely the absolute difference in the number of heads and tails will become large as the number of flips becomes large. That is, the probability that the absolute difference is a small number approaches 0 as the number of flips becomes large. Also, almost surely the ratio of the absolute difference to the number of flips will approach 0. Intuitively, expected absolute difference grows but at a slower rate than the number of flips, as the number of flips grows. History. The Italian mathematician Gerolamo Cardano stated without proof that the accuracies of empirical statistics tend to improve with the number of trials. This was then formalized as a law of large numbers. A special form of the LLN was first proved by Jacob Bernoulli. It took him over 20 years to develop a sufficiently rigorous mathematical proof which was published in his Ars Conjectandi in 1713. He named this his Golden Theorem, but it became generally known as Bernoulli's theorem. This should not be confused with the principle in physics with the same name, named after Jacob Bernoulli's nephew Daniel Bernoulli. In 1837, S.D. Poisson further described it under the name of La Loi des Grands Nombres. Thereafter, it was known under both names, but the law of large numbers is most frequently used. After Bernoulli and Poisson published their efforts, other mathematicians also contributed to refinement of the law, including Chebyshev, Markov, Borel, Cantelli and Kolmogorov and Keynesian, who finally provided a complete proof of the LLN for arbitrary random variables. These further studies have given rise to two prominent forms of the LLN. One is called the Wick law and the other the Strong law, in reference to two different modes of convergence of the cumulative sample means to the expected value. In particular, as explained below, the strong form implies the weak forms. Two different versions of the law of large numbers are described below. They are called the strong law of large numbers and the weak law of large numbers. Both versions of the law state that, with virtual certainty, the sample average converges to the expected value where x1, x2, is an infinite sequence of i.d. Lebesgue integrable random variables with expected value equals micro. Lebesgue integrability of xj means that the expected value e exists according to Lebesgue integration and is finite. An assumption of finite variance var equals sigma 2 less than infinity is not necessary. Large or infinite variance will make the convergence slower, but the LLN holds anyway. This assumption is often used because it makes the proofs easier and shorter. The difference between the strong and the weak version is concerned with the mode of convergence being asserted. For interpretation of these modes, see convergence of random variables. Weak law. The weak law of large numbers states that the sample average converges in probability towards the expected value. Proof, that is to say that, for any positive number epsilon. Interpreting this result, the weak law essentially states that for any non-zero margin specified, no matter how small, with a sufficiently large sample, there will be a very high probability that the average of the observations will be close to the expected value, that is, within the margin. Convergence in probability is also called weak convergence of random variables. This version is called the weak law because random variables may converge weakly as above without converging strongly as below. Strong law. The strong law of large numbers states that the sample average converges almost surely to the expected value, that is, the proof is more complex than that of the weak law. This law justifies the intuitive interpretation of the expected value of a random variable when sampled repeatedly as the long-term average. Almost sure convergence is also called strong convergence of random variables. This version is called the strong law because random variables which converge strongly are guaranteed to converge weakly. The strong law implies the weak law but not vice versa. When the strong law conditions hold, the variable converges both strongly and weakly. However, the weak law may hold in conditions where the strong law does not hold, and then the convergence is only weak. There are different views among mathematicians whether the two laws could be unified to one law, thereby replacing the weak law. However, the strong law conditions could not be proven to hold same as the weak law to date. The strong law of large numbers can itself be seen as a special case of the pointwise ergodic theorem. Moreover, if the summands are independent but not identically distributed, then provided that each xk has a finite second moment, and this statement is known as Kolmogorov's strong law, c.e.g. Sen and Singer. Differences between the weak law and the strong law. The weak law states that for a specified large n, the average is likely to be near mu. Thus, it leaves open the possibility that happens an infinite number of times, although at infrequent intervals. The strong law shows that this almost surely will not occur. In particular, it implies that with probability 1, we have that for any epsilon greater than 0 the inequality holds for all large enough n. The strong law does not hold in the following cases, but the weak law does. 1. Let x be exponentially distributed random variable with parameter 1, the transformation with the following expected value. 2. Let x be geometric distribution with probability 0.5, the transformation with the following expected value. 3. Uniform law of large numbers. Suppose f is some function defined for theta and continuous in theta. Then for any fixed theta, the sequence f will be a sequence of independent and identically distributed random variables, such that the sample mean of this sequence converges in probability to f. This is the pointwise convergence. The uniform law of large numbers states the conditions under which the convergence happens uniformly in theta. If theta is compact, f is continuous at each theta for almost all x's, and measurable function of x at each theta. There exists a dominating function d such that d less than infinity, and then f is continuous in theta, and this result is useful to derive consistency of a large class of estimators. Borel's law of large numbers. Borel's law of large numbers, named after Emil Borel, states that if an experiment is repeated a large number of times, independently under identical conditions, then the proportion of times that any specified event occurs approximately equals the probability of the event's occurrence on any particular trial. The larger the number of repetitions, the better the approximation tends to be. More precisely, if E denotes the event in question, P its probability of occurrence, and N the number of times E occurs in the first n trials, then with probability 1, Chebyshev's inequality, let X be a random variable with finite expected value mu and finite non-zero variance sigma 2, then for any real number k greater than 0. This theorem makes rigorous the intuitive notion of probability as the long-run relative frequency of an event's occurrence. It is a special case of any of several more general laws of large numbers in probability theory. Proof. Given x1, x2, an infinite sequence of i.d. random variables with finite expected value E equals micro less than infinity, we are interested in the convergence of the sample average. The weak law of large numbers states. Theorem. Proof using Chebyshev's inequality. This proof uses the assumption of finite variance. The independence of the random variables implies no correlation between them, and we have that the common mean mu of the sequence is the mean of the sample average. Using Chebyshev's inequality on results in this may be used to obtain the following. As n approaches infinity, the expression approaches 1, and by definition of convergence in probability, we have obtained proof using convergence of characteristic functions by Taylor's theorem for complex functions. The characteristic function of any random variable, x, with finite mean mu, can be written as all x1, x2, have the same characteristic function, so we will simply denote this phi x. Among the basic properties of characteristic functions there are if x and y are independent. These rules can be used to calculate the characteristic function of in terms of phi x. The limit EIT mu is the characteristic function of the constant random variable mu, and hence by the Elliott Vy continuity theorem, converges in distribution to mu. Mu is a constant, which implies that convergence in distribution to mu and convergence in probability to mu are equivalent. Therefore,